Hello, welcome to Practicing Special Limits. We discussed all 5 wonderful limits. I exactly proved them, and I would like now to solve a number of interesting problems where we'll use all applications of those 5 special limits. The example number 1, limit of sine 4x over sine 5x when x goes to pi is equal to. So when x goes to pi, sine of 4 pi is 0 and sine of 5 pi is also 0. It's 0 over 0 in determinant form. And you remember, special limit sine x over x is also 0 over 0, and that is the case where I will try to reduce it to the special limit number 1. First of all, x is approaching to pi. The special limit number 1, my variable is approaching to 0, which means I need to probably introduce a new variable which will approach to 0. As you can see, x minus pi approaches to 0, which means I will probably introduce a new variable. Let's say let y is equal to x minus pi. Would be my y, because I want my y to approach to 0, my variable approach to 0, to be consistent with the limit number 1. In other words, x from this transformation will be equal to y plus pi. I will use that substitution for my limit, and it will be equal to the limit of sine 4x. X is equal to y plus pi. So 4 multiplied by y plus pi. So 4y plus 4 pi over sine of 5x, which is 5y plus 5 pi. 5y plus 5 pi. Now my y goes to 0. I have a new transformation, new variable, y goes to 0. And it's equal to, now let's simplify it. 4y plus 4 pi is exactly 2 complete circles. You wind up at the same point, so we can just drop it. 2 complete cycles. So it's a limit of sine of 4y over y goes to 0. Sine 5y plus 5 pi. 5 pi is exactly odd number of half circles, so you wind up at the opposite point, exactly on the opposite side along the diameter, and that point will have the opposite sign of the sine function. So in other words, it will be equal to minus sine of 5y. We can drop 5 pi while introducing a minus sign up front. Will be the opposite value. And it's equal to, now it's getting easy, minus up front. So it's a limit. Y goes to 0. It's sine of 4. The answer is minus 4 over 5. I'll just do it in more detailed state. So it's 4y over, I can divide it by y and multiply it by y to preserve the value. That's sine 5y. And here I have the 2 consequences of the first limit. This goes to 4 and this goes to 1 over 5. 1 over 5. Okay. With the minus sign up front. With the minus sign up front. Again, this is easy to prove. Any calculus books, everywhere you will find sine ax over x, where a is the constant when x goes to 0, is equal to the constant a, which is 4 in this case. This goes to 4. Yeah. and this is 1 over 5. So finally, the result is minus 4 over 5. That's the answer for the example 1. I hope that's clear. Example 2, the limit of the difference of the roots over tangent squared 9x. If you remember when I was proving the wonderful limit number 1, I said there are many ways to resolve the indeterminate forms. That's also a 0 over 0 indeterminate form. And one of the common ways when we have fractions, rational functions, it's kind of a mixture of rational and transcendental. So one of the ways to resolve it is to multiply by the conjugate factor. In this case, you can clear up the radical signs. So I can just multiply by the sum of those two roots. It's a limit. X goes to 0. If I multiply by the sum of those roots, both numerator and the denominator, will be square of that minus square of that. The radicals will be cleared. And I will have just 1 minus x sine 2x minus cosine x over tangent squared 9x. Also, I need to multiply it by the conjugate factor of the two radicals, 1 minus x sine 2x plus the radical cosine x. This one, yeah? Multiply both by the plus. That's the conjugate factor, and when x goes to 0, this is to see cosine 0 is 1, root of 1, 1. This drops, root of 1, 1. 1 plus 1 is 2. Everything goes to 2. That's equal to 2. And so 1/2, we can pull it up front. 1/2, it's a constant in front of the limit. And it's equal to the limit. Again, 1 minus cosine x. We proved it in trigonometry. You all know it. It's a basic trig formula. 1 minus cosine x is equal to 2 by sine squared x over 2. You all remember that formula. When x goes to 0. And here I have 2 sine squared x over 2 minus x sine 2x over tangent squared 9x. Now this 2 is up front. Yeah. So I'm trying to reduce it to my special limit number 1. What if I divide both numerator and the denominator by x squared? Because sine is squared here, so I need my argument squared. Let me do that. So in other words, 1 over x squared, 1 over x squared. This is what I will do. I will multiply both by 1 over x squared is a non-zero value. I can do that. X is approaching to 0. It's never equal to 0. It's just approaching. So it's non-zero value. I can multiply both numerator and the denominator by non-zero value. So it's 1/2. That's the limit. Here I have sine x over 2 over x over 2 over x and another x. Another sine x over 2 over x. As you can see, sine x over 2 over x, and this 2 goes down here. Second sine x over 2 over x, no 2. So I just divided by this x squared, yeah? I also need to divide this term by x squared, which is minus sine 2x over x. X and 1x reduced fraction with sine 2x over just 1x. And everything is over. It tangent 9x over x by the tangent 9x over x. Yeah, just divided by x squared. Yeah, it's getting simple now. You can see it. X goes to 0. I have my wonderful limit number 1. X over 2 also goes to 0. So sine of x over 2 over x over 2. This goes to 1. This goes to 1/2 because it's x 1/2 coefficient. I'm divided by x, not x over 2 in this case. It's easy to show, easy to prove. So it's actually equal to 1 over 2. Fraction here, 1 by 1/2 minus sine to x over x is just 2 when x goes to 0. It's just this coefficient again. It's easy to show it, easy to prove it. Every calculus book shows that explicitly. So it's minus 2, and the same tangent 9x over x is 9 by 9. And tangent 9x is sine 9x over cosine 9x. Over x, sine 9x over x, that limit goes to 9, cosine 9x, x goes to 0 is 1. So 9, and again, easier to show, any book has that. So it's just equal to what I have here. This is minus 1/2 minus 2 is minus 3/2, and 2 by 81 over 81 by 2 is 162. So in other words, it's minus 3 over 324. You can reduce that fraction, and it will be actually equal to, and it's equal to minus 1 over 108. Yeah, you can just reduce this fraction, and the answer is minus 1 over 108. Next example 3. I have sine x over sine of 2, however 1 over x minus 2, x goes to 2. Looks like we have sines, you might think it's sine x over x, first limit, and actually this is 0 over 0 indeterminate form. And here we have different kind of indeterminate forms. Sine 2 over sine is 1 to the power of infinity. It's a different nature limit. And I said that the second wonderful limit actually helps us to resolve those kinds of indeterminate forms, 1 to the power of infinity. So I will use my second special limit in this case, which is equal to, I can write limit x goes to 2. I can also write that it's 1 plus 1. So I need 1 plus sine x over sine 2 and minus 1. I'm trying to be consistent with this pattern. So that's the value which goes to 0. Yeah, sine 2 over 1 minus, this goes to 0. That's the infinitesimal value. And I have this power of 1 over x minus 2. Now, if I have this value, I need to take the reciprocal of that value, which is not there. So I will use the reciprocal of that value. So it's equal to the limit of x goes to 2, 1 plus sine x over sine 2 minus 1. And I need to raise it to that reciprocal of that power. So it's 1 over sine x over sine 2 minus 1. Yeah, but I never had that power before. I will compensate it by taking the reciprocal. So sine x over sine 2 minus 1. And finally, I will have my original power 1 over x minus 2. I hope that's clear. A lot of nesting here, but I just came to this wonderful limit number 2. This value is approaching to e. It's this case. Yeah? It's an infinitesimal value, 1 over small infinity. So that's exactly 1 to the power of infinity. It gives me e. Let me continue the next line, and it's equal to, and again, it's a limit. My x goes to 2 now. I have e to this power, yeah? E to sine x over sine of 2 minus 1 and power 1 over x minus 2. Since e is a continuous function, I can interchange the function and the limit. So in this case, it will be equal to e to the power of the limit when x goes to 2, and the limit of what? It is sine x minus sine over 2 over sine 2, and multiply by x minus 2. And just multiply powers, the power rule, and that's the limit of that. Now, here I have the difference of the signs. It's also basic trig formula. We all know it, and we all remember it, that sine x minus sine 2 is equal to 2 sine x minus 2 over 2 plus cosine x plus 2 over 2. This is what I will use here. Sine of 2 is a constant. I can pull it up front of the limit. So it will be equal to e 1 over sine of 2. And here the limit, x goes to 2. And then 2 sine x minus 2 over x minus 2 over x minus 2. Yeah. This is 2 sine x over 2 x minus 2 over 2. Just follow that formula. 2 sine x minus 2 over 2, and also multiplied by the cosine of x plus 2 over 2. I hope that's clear. This is over 2. And again, x goes to 2. I have here the value x minus 2 goes to 0. It's now reducible to the special limit number 1. Actually, this example encompasses two special limits, the special limit number 1 and the special limit number 2. It happens a lot. So sine x minus 2 over 2 over x minus 2 is actually this constant 1/2. Yeah, that's the same one. So 1/2 by this 2 is just 1. So it will be 1 here. And the limit of cosine 1, again, this goes to 1/2, and this 1/2 multiplied by this 2 will be 1. And cosine 1, x goes to 2, will be cosine 2 plus 2, 4 over 2, will be cosine 2. It's a constant, so it's equal to e of cosine 2 over sine 2. So which is equal to e of cotangent of 2. The final answer is e to the power of cotangent of 2. I have used all my space on the board. I hope that was clear, interesting, informative. Now you know that when you solve limits, sometimes you need to manipulate not just one, many of them. I hope to see you soon in the next video, where I will continue my discussion solving more problems using more special limits. Thank you very much. See you soon. Bye bye.